I'm Dan Olds, and this is the next to the last stop on my grand 2018 HPC Road Trip, and we're up here at the beautiful Lawrence Berkeley National Lab, and we have our subject in front of us. Please introduce yourself.
Hi, I'm Glenn Lockwood. I work at the National Energy Research Scientific Computing Center, or NERSC, here at Berkeley Lab. I work in our Advanced Technologies group, and I specialize in parallel I/O and large-scale storage systems.
Parallel I/O, pretty complicated stuff. What are you working on?
Well, I'm tasked with figuring out what the future storage systems of the world have to look like. So our laptops now have SSDs in them. They used to have spinning disks in them, and the same is true of supercomputers. So there will come a day, we think, when supercomputers of tomorrow won't have any spinning hard drives in them. They do today, but for the same reason we don't like them in our computers, we don't really like them in supercomputers. They're large, bulky, mechanical, hot, and they're not as fast as flash devices. So I work in the general space of trying to figure out how best to incorporate flash in next generation systems and help our users store and recall their data faster than they could before.
Now, the other thing that's happening is that our traditional data protection is breaking down because we have so many drives and they're so big. When you're starting to talk, a 5-10 terabyte drive, that takes a long time to rebuild.
It certainly does.
And when you have so many drives, you can have multiple failures at the same time. How do we get around that?
That's an open question of research, right?
You haven't figured that out yet? You haven't fixed it?
There are some canned answers. There are technologies like Clustered Parity, if you've heard of that. So this is where you break down the idea of storing, one piece of one data on a single drive. Rather, you store multiple pieces of multiple data across multiple drives, and you leave a bit of every drive empty so that if one fails, you can rebuild to all of the drives at once. So it's
sort of a very big picture RAID.
Yes, yes. So it helps rebuild things faster, it helps things move a lot faster, but it does require a lot more computation to do that. So the rebuild process is a lot more CPU intensive, and it does change what conventional wisdom on how fast a system that is supporting RAID can go. You have to design all the other components around the storage a little differently to make sure that this new declustered scheme is not impacting your performance adversely.
What are the other bottlenecks that keep you up at night?
So IOPS are a big one. So this is how fast you can issue individual read and write operations to storage. We're seeing a lot of workloads coming in from the experimental and observational data sources that once upon a time could simply be satisfied on computers that were close to, say, the microscope or the telescope that was generating data. But the resolution of those devices have gotten so high that they're coming to us, and they have to rely on our large-scale storage and compute resources to process their data. And the workloads they're bringing us are very different than what we've seen in the past with traditional large-scale simulation. So their I/O patterns are a lot more challenging, and as a result, they're asking for performance in different dimensions than what we've traditionally been able to provide with just spinning disks.
A lot of very high ingest.
Yes, high ingest, and the way they analyze their data is not nice and deterministic like it has been with a simulation. With a simulation, the most taxing workload is you just save all of your data at once. This is like saving a very big Word document. It's actually, from an I/O perspective, pretty easy to do. But what the experimental folks do is they don't know what processing they have to do until they look at the data. So they're often chasing bits of data around in their data files, which generates a lot less coherent I/O traffic than before. And hard drives just aren't designed to do that very well.
So will SSDs help that, flash memory?
SSDs will help tremendously. So we're reaching a point when the cost of SSDs on a performance basis is overpassing the cost of performance on spinning drives. So we incorporated SSDs into our current generation supercomputer here at NERSC called Cori as a burst buffer. And then underneath that, we still have spinning disk. And then our next generation system that we just announced, Perlmutter, which we'll be delivering in year 2020, we will have all flash.
And that's quite the system.
It is. We're very excited about that.
Yeah, that's big.
It is, and it'll be the first HPC system that has been designed from the ground up to support both data-intensive workloads as well as the traditional large-scale simulation and modeling workloads that we've had in the past.
Exciting. Who's doing that system for you?
So Cray is our integrator partner on this system.
Okay, that's what I thought. Very cool. Very good stuff. Anything else I should know?
I don't think so.
Well, NERSC is now a net importer of data, whereas most centers are exporters. but they actually
Really?
import more data through the observational thing, so you might want to talk about
Sure.
that.
So like John said, NERSC is, we receive more data than we send out to the world. So we're in a data sink, and there's a lot of factors that contribute to that. So there are a lot of experimental and observational instruments out there, many supported by the DOE, that are sending their data here to be processed, and then they're processed here, and the idea of that processing is to reduce the data into a more distilled version of exactly what they want and nothing else.
And you're in charge, your folks are in charge of that at NERSC,
We
to distill that down?
No, so
they distill it?
the scientists run on our system. So we provide the hardware
You provide the
resources,
okay.
as well as the storage resources. They do the data reduction here, and the net results are what are exported. So as a result, we take in more data than we send out.
How much data do you handle, roughly?
Quite a bit. So at rest,
Okay, quite a bit, that's all we're looking for.
It's actually quite a bite.
Oh, it's quite a bite, okay.
it's so just a few numbers. We've got 150 petabytes of data sitting on tape right now, and that number grows quite a bit, just month over month. In terms of our file systems, we see in the order of a petabyte read and written on every single day on our Cori file system. So this is our current generation large-scale supercomputer. And I'm not too sure about the networking, but hopefully Eli has some indication of that. But it
As he
is,
takes a sidelong glance at Eli.
but it's on the order of hundreds of terabytes to petabytes per day of data moving around our data center.
Okay, we are still at Lawrence Berkeley National Lab, and we're talking to Eli Dart, who does something with computers, I believe.
A little bit with computers. I do a lot more with networks.
Networks.
So I work for the Energy Sciences Network, or ESNet.
Oh.
So ESNet is a nation-scale, high-performance fiber optic network that interconnects the entire DOE National Laboratory Complex. We
Really?
connect the labs to each other, the facilities to each other, and we connect them to the outside world, both the other science networks in the US and globally, and to the rest of the internet. We've been
That
doing this for a very long time.
Incredible. That's a big job.
It is. It is. I mean, running a supercomputer center is a big job too. This is related but different. And I would say actually synergistic. So Glenn was talking earlier about the data coming into NERSC from experimental and observational facilities. We're the means by which that actually happens.
So throw me some stats. What are we looking at in terms of data flow and that sort of thing across your network?
So, I mean, the answer is always it depends.
Of course, yeah.
Right? Right, context matters. So in terms of aggregate volume, I think we carry on the order of 80 petabytes a month. In terms of how fast any particular data transfer can go, it depends a lot on the storage systems, as Glenn described, that are actually at the ends of the transfer. But if those things are configured well, we can traverse coast to coast at multiple gigabytes per second.
Wow.
Oh yeah. Oh yeah. I mean, and there's a bunch of engineering that goes into
Of course.
making that possible. Just like you wouldn't stand up a supercomputer, take all the defaults, and just turn it on. Oh yeah, and we'll go with that, right? There's a lot of engineering and testing and tuning and making sure that it actually behaves in the way that you want it to behave.
Speaking for myself, I might do it that way, but the rest of you wouldn't.
You might do it that way to start, but it wouldn't pass spec, right? So,
True.
And so for large scale data transfer, it's the same sort of thing, right? It takes a lot of proper engineering to get it to do what you need to do. Once you get that engineering work done, you now have a scientific capability that makes all of the individual pieces of the US science complex much more effective. It's a network effect just like any other. Right? So you can think of ESNet as the circulatory system for data within the DOE, right? And specifically for the DOE Office of Science.
What are the big challenges?
Wow, there are several of them. Let's see. So one is simply the set of exponentials that we have to ride, right? So we live in an exponential world. Humans are not exponential entities, right? I scale very, very, very badly in an exponential environment. I really do. So what we need to do then is be able to get the data where the data needs to be while it's growing exponentially, without also growing the amount of human effort required in order to get the science done, right? Because as soon as you tie human effort to data scale, you just lose. Right? So a big chunk of how we make sure that we're doing well is that scientists are able to handle megabytes, gigabytes, terabytes, petabytes, and higher without having to go through a bunch of extra rigmarole and shenanigans just to get their jobs done. Because at the end of the day, nobody wants to spend a huge amount of time on data movement,
Yes.
right? They want that to be done so that the data can be where it needs to be in order for productive scientific analysis to occur. Because that's where the gold is.
Yeah.
Right.
So moving in, when you can, move the compute to the data as opposed to the data to the compute.
Absolutely. And in fact, so from my perspective, we support both in the general case. And we have to. Because sometimes you've got this huge data store and you've got a compute resource right next to it. The scientist has permission to run there, move the code there, do it. And this is actually even true of automated systems too. There are automated systems that know how to do job placement next to data and so forth. Sometimes you can't do that. And if you can't do that, well, then you need to do data placement. Right? Mm-hmm. So you have to then put the data next to the compute resource where the scientist has permission to run, or where their code's actually optimized, because different systems have different architectures, right? Different systems are more or less well suited to different types of codes and different types of analysis.
Some have GPUs, some accelerators, other accelerators, and
That's correct.
They are best fit for that workload. So you've got to move the data to those systems regardless of the cost.
Yes, that's right. And I mean, in fact, scientists also typically get an allocation on a named resource. Mm-hmm. And so if you have an account at NERSC and your data is sitting at NERSC, great, go for it. If you have an account somewhere else where you generated all your data and you now get an allocation at NERSC, well, in order to beneficially use that allocation, you have to do data ingest to the NERSC storage system in order to be able to do that. Right? Same is true for any computing facility.
Sure.
And so now if you want to talk about an experimental workflow, right, you have to tie a bunch of facilities together. So you've got the experimental facility that's running. You have a supercomputer center when you want to analyze the data. You glue those things together by means of a high-performance network, and now that gives you this integrated thing that you can drive as one scientific instrument. Right? That's the future for the experimental and observational folks, because all of their sensors and microscopes and all the things that they've got, they're also on this exponential growth curve. So they're now far beyond the kind of computing that, well, their needs cannot be served by the compute that they can stand up next to their experiment. In many cases, they don't have the rack space, they don't have the power and cooling, and they don't have the people.
That's a good point.
Well, so think about what a high-performance network or a supercomputer center actually are, right? It's a bunch of hardware, it's a bunch of software, right? It's a bunch of kit. It's also a bunch of people who understand how all of this stuff actually works for real and can drive it effectively. Right, so that human capability is really important, because that's what then makes all of that kit an effective scientific tool, because I can talk to you, scientist, and figure out what you need, right, how you need to drive this thing, and then you say, okay, here's what we need to do, I can help you do it, show you how, right, show you how to use scalable tools to do it, and now suddenly you've got this thing that you didn't have before that allows you to do things that you couldn't do before. That's a big part of what the National Laboratory Complex is for.
I see. So sort of a centralization of skills and experience and capabilities.
Yes.
To be able to allow the scientists to achieve their goals.
Yes, it's a capability for the country, absolutely.
What keeps you up at night?
What keeps me up at night? Falling behind. I mean, we've got to stay up on it, right? Like I said, we live in an exponential world. As soon as you fall behind, you're done.
Yeah.
Right? So.
Yeah.
But what gets me up in the morning is supporting the scientists, right?
Okay.
So we can meaningfully contribute to the discoveries that are going to help fix the very real problems that humanity faces. Right? And there's a bunch of them. I could list them. You know what they are.
Sure.
Right? Fresh water, disease. Right? There's all of these things that we have to collectively as humans fix. And I don't have the math to be a real scientist, okay? I just don't. But in this way, I can contribute.
So one of the things we want to talk about is this data movement record, where SLAC at Stanford moved a petabyte of data in, what, 29 hours?
Yeah, so the setup for that, they were using a network engineering and virtual circuit service that ESNet developed called OSCARS. OSCARS won an R&D 100 award. It's something that we use for.
And you played a key role in developing that.
No.
Sure you did.
No. Credit where credit is due. Chin Guok was the lead for that.
Okay.
Vangelis Kaniotakis was one of the primary developers. Several other ESNet staff have contributed far more meaningfully. Now, I've been an Oscars user, and I've helped science.
Well, good job on doing that.
I've helped science collaborations, get onto it and so forth. But the idea there is that it provides bandwidth and service guarantees for traffic that matches the profile of what should go into that virtual circuit.
Okay.
This has been used extensively to support the LHC experiments and also to do the kind of experiments that are necessary for doing a light source upgrade, right, or something like that. So in this case, at SLAC, they're upgrading the LCLS, which is a line-at coherent light source. It's a free electron laser. And they're able to do amazing things with it already today. After the upgrade, it's going to get a lot better because, well, it's going to be upgraded. The consequence of that is going to be a drastically increased data output. And so there's a whole bunch of work going on to figure out what the right methodology, what the right stack is for managing that increased data output. At least some of it is going to involve bringing some of that data to supercomputer centers. Like NERSC. We've already run experiments for that and done several test runs, at least one of which I think ended up being published in Nature. So again, this is connecting scientific facilities together by means of a high-performance network, right, to get stuff out of your experiment that you otherwise would not be able to do. But ESNet brings several tools and technologies to the table, right? It's not just dumb pipes and plumbing, right?
Yeah.
It's people expertise, architecture, design, and so on. So there's a design component of some of these things called the Science Dmz Model, which is a way of architecting essentially the network front end for a scientific facility or a supercomputer center or a user site, a university, that allows for the high performance data flows to be engineered for separately from the commodity network at that site. So if you think about what's the internet today, right? The internet of today for most people, and certainly for most business users, is like the phone company network, right? The phone network of the 1970s, right? Its job is to do the same thing tomorrow as it did yesterday, and to not go down between yesterday and tomorrow.
Exactly.
That's it. So in the high growth, fast-paced world of scientific innovation, that's too slow, both in terms of bit rate and in terms of innovation rate. And so what the Science Dmz model allows us to do is to break out the high-performance data transfer assets for a site and engineer for that in a way that doesn't cause undue harm to the commodity network, which has to stay up and be stable and have all the same services and be secured because of all the laptops and phones and financial systems and all that stuff that lives over there, right? And it puts the high-performance data assets in their own enclave where we can deal with them effectively and innovate quickly. Because, like I said, if we fall behind, that's kind of a problem.
Can you explain what we've got up here?
Yes, so this is the my.es.net portal. It shows the roughly current state of traffic load on all the different links in ESNet. Now, this has been simplified for readability. So there are a lot more connections actually in the network than exist on this map. But if you made it an accurate engineering drawing, it would be really hard to get a handle on what you're looking at. So this is a balance of just for simplicity. I mean, we have real engineering drawings, obviously.
Sure, of course.
But they're really, really complicated. So for example, most of the big labs here, Fermi, Argonne, NERSC, Livermore, right? They all have multiple connections to ESNet, and that's not shown here, right? That's shown up, it's rolled up in an aggregate. So, so if I go, Fermi's a big LHC site, for example. If I click on this, there's this list of connections over there on the right where it says interfaces. All of that is rolled up into this one.
Okay, that's all Fermi then.
Yeah, that's all between Fermilab and ESNet.
Okay.
Right, and so similarly, some of these links here are, well, this one's only got one, but there are some that are. Let me find one that's got multiple links on it. Chicago to Washington, maybe.
Anyway, another question.
No.
Why is ESNet at Berkeley Lab and not at one of the other
Yeah. Why is ESNet at Berkeley Lab and not at one of the other labs?
ESNet came to Berkeley along with NERSC from Lawrence Livermore in 1996.
Okay.
That was before my time. I don't know why the decision was made. But ESNet is a scientific facility, right? We're a DOE Office of Science facility in the same way that NERSC is a DOE Office of Science facility, and in the same way that the supercomputer centers at Argonne and Oak Ridge are, the same way the Advanced Light Source here, the Advanced Photon Source at Argonne, the LCLS at SLAC. They're all DOE Office of Science facilities. All the facilities are, well, almost all. DOE facilities are typically housed at one of the national laboratories. It's one of the main functions of the National Laboratory Complex is to build and operate these big scientific facilities, which are an integral part of the U.S. science complex. Mm-hmm. And so this is part of our mission for the country, is to run those scientific facilities. ESNet is a facility like any other, so it's headquartered at a national laboratory.
Now, looking back at the application here, what are we seeing at the bottom? Is that the data that's currently going through the selected links?
Yes, that's correct. So
what's the scale there? Can't quite see.
Okay, so on the y-axis here, there's two directions, right? So this is between two of our core router sites.
Okay.
CHIC is short for Chicago. WASH is short for Washington, D.C.
Okay.
And so the blue is between Washington and Chicago. The orange is between Chicago and Washington.
So Chicago to Washington.
Right.
And Washington to Chicago.
Because all network links, all our network links are full duplex, right? So there's traffic flowing in both directions at any given time, and there's no guarantee that that traffic is symmetric in load.
Okay.
So if you look at this, there's a lot more traffic going from Chicago to Washington than there is going from Washington to Chicago.
And
in 10 minutes it could change, right?
Is that gigabits or gigabytes?
So this is one of the funny things. Networking people think in bits, storage people think in bytes. Whenever Glenn and I have a conversation, we have to make sure to take a factor of 8 into account.
Yes.
Right, so it's just something that you get used to doing. But this is in bits. So here's the 0 line. Each of these tick marks is 10 gigabits per second.
Okay.
So somebody, and you see this lump right here, that's a big data transfer that somebody did, most likely. So somebody moved a big chunk of scientific data, probably multiple terabytes, at about 40 gigabits per second, from someplace to someplace, but it traversed that link between Chicago and Washington. So this is the 40 gigabit line here. There's this little peak almost made it to 50 gig. The LHC experiments will run at over 60 for hours at a time.
Wow.
The physicists move a lot of data around.
And that data could have come from the West Coast going to someplace on the East Coast, but it's simply using that Chicago to Washington link.
That's correct.
As the most efficient route.
Right. That's right. That's right.
Very cool. And so I'm sure you have people monitoring this, or machines monitoring this, to see if there's any problems.
Right. We have people and machines monitoring the network 24/7.
Okay.
Absolutely.
That would make sense. That's the way I would do it. Very cool. Thank you for the demo.
You are most welcome.
Do you want to call up NERSC?
Yeah, so there's
we'll take a look at NERSC.
The NERSC portal is here. So this is a display of what's currently computing on the NERSC machines.
No, but I mean
Okay.
the NERSC link.
Oh.
On my guess.
You can do that.
So what happened, Dan, is that NERSC.
Let me get you a little bit closer.
Part of NERSC.
Okay. You have a special guest now. Introduce yourself to the crowd.
This is John Basher with communications at NERSC and ESNet. What happened is when NERSC first was created back in 1974, the users communicated with the center using, they'd call up on phone lines, the old Mickey Mouse ear modems. And so over the years, as more users were using NERSC and there was more need for data going in and out, the networking effort just grew up as part of the engineering group as part of NERSC. And over the years, they used satellite links, they used landlines, they used any number of different things. And it was all to support magnetic fusion energy research. And at the same time, DOE also had a high energy physics network. And in 1986, they made the decision to merge those two networks into one, and that's what became ESNet. And ESNet was created in 1986, and then in 1988 actually began providing unified support for all the Office of Science offices.
Okay.
And then it was still a department within the NERSC organization. So when they moved, it made sense to move both of them here to Berkeley from
Good.
Livermore.
Makes sense. Highly efficient. So we're looking at the NERSC.
So this is the NERSC link. And so as happens with network traffic diagrams, sometimes you'll get a couple of big spikes that squish everything else down. So it looks like there isn't actually a whole lot going on, but that's because way over here on the left-hand side, there was a data transfer that ran at, if my eye is correct, ran at least 80 gigabits a second. Into the, and that was data ingest, right? So that's from Sunnyvale to NERSC. And there's another transfer there that went at over 40 gig just recently. So it very much depends on, when you look at these graphs, you really have to check the scale to figure out what you're looking at. Because you can easily go, oh, well, there's nothing here. Well, no, actually, there's just something really big that's made the scale auto-adjust. I mean, the image rendering libraries here just auto-adjust for whatever the data is.
Sure. And right now that data is probably being crunched on at some site. where the
Entirely
compute is.
possible. Or somebody moved a data set in and then launched a NERSC job against it.
Okay.
Right?
Yeah, it makes sense.
And as Glenn mentioned earlier, one of the core ideas in data analysis, right, is you take whatever your data set is and you derive higher value data products from that allow you to gain greater scientific insight, right? And so a bunch of the work that gets done on something like this is you say, okay, well, I've got all this stuff. I need to figure out the answer.
Yeah.
Right? I need to do something useful with this, and so I integrate it all, potentially with data from multiple sources, in fact. And then I end up with something that I could not otherwise do on my laptop or my local cluster or whatever.
Fantastic demo. Thank you for taking us through that.
You're most welcome.